61A Lecture 33 Q&A. Yeah, so we've come to the end of required content. There wasn't a whole lot in today's lecture. It's an important concept to figure out how to interleave aggregation with all the other stuff you've learned, joining and filtering and all that. And I think it does show up a lot in like practical SQL, that you do a fair amount of grouping and either summing or maxing.
I think that's a big part of sort of data analytics, is just being able to query the database. Like, what I'm looking for this, and what about this, and what about this, and that kind of just being able to poke at your data and understand the landscape is, I think, probably one of the most important or widely used applications.
Yeah, and it definitely takes practice. It's just like, you learn what a while statement is and an assignment statement is. That doesn't mean you know how to do everything that you can do with those, right? And so now you know kind of all the primitive parts of a standard select query, which is kind of the main way that you access things in a database. And you just have to practice a little bit to learn how to get exactly what you want out of any given data set.
Yeah, every time I write a SQL command, it takes me like 5 iterations to get all the little pieces exactly right. But as
Right,
long
and
as you
people
know what,
do, yeah, people write these kind of interactively, right? That's kind of how
yeah,
it's set up. So maybe you only run it on a sample of the data if you have a huge data set, but you often do kind of look at the result and say like, oh, does that actually make sense, or did something go
yeah,
wrong along the way?
yeah, exactly.
The first question was about whether when you aggregate and you also select an individual rows value, like for example, you take the max legs and you also want the name of the animal that has that many legs, how do you know which one you're going to get in a tie?
I don't know the exact answer to this. Maybe John does, but I think it depends on the underlying implementation, which SQL implementation you're using.
Yeah, that's right. I mean, SQL doesn't give you any kind of standard for what happens when you aggregate, and yet you also select some element that's not aggregated. Um, SQLite's pretty reliable with max in that it will give you some max, but I don't think it gives you any guarantees about which one.
Yeah.
And if you write a longer query, you can get a lot of control, right? So you could write a longer query that says, first I want to compute the max, and then I want to find all the rows that have that max, and then I want to pick the order for them. And so if you're kind of willing to write something more elaborate, then you can know exactly what you're going to get. So in general, you should not rely too much on this shortcut of, you can select a non-aggregated value along with an aggregated value, because you might not know exactly what you get, and it's sort of better to write something longer and get control.
Yeah.
Now,
And you definitely shouldn't assume, just because you see a particular sort of side effect behavior, don't assume that that will always work. First of all, the language will evolve and change. There'll be different SQL implementations. And so, if it's not defined, I actually think it's a bad thing that SQL lets you get away with this. Yeah. Um,
right, and
yeah.
yeah, there's certainly a good argument that we shouldn't have even taught you the fact that this works, because maybe you'll rely on it and it won't work in some other implementation of SQL. But yeah, the one thing that we don't really cover in this course, but is covered in more advanced courses, is that sometimes you have a query that has another query embedded in it. So like, how would you get the max and then use that max to do something else? This actually does show up in some real world SQL programs, that you kind of have nested queries inside of queries inside of queries, and they get really huge. You'll see some of that if you take, for example, data 100, but we had to pick a boundary here, and so that's kind of where we stopped. Yeah, good question. So kind of when do you use list and when do you use cons in some recursive procedure like zipping or something like that? It's always good to remember what they do. So list builds a new list where you have the elements and you're putting them into a list. And cons builds a new list where you have most of the list, the rest of the list, and one new element. And you're building a new list out of an existing list by adding one thing to the front. I think one way to check your work is that if you ever have some procedure where, somewhere in the middle of it, you have a recursive case that looks like list. You should know that since this takes 2 arguments in your code, it's always going to build a list of length 2. So if you're ever trying to build a list that's arbitrarily long, like it depends on the input, then list isn't going to do the trick. List is really only there to build lists of a particular fixed length. You can build a list of length 3 like that, but you would never have this piece of code building a list that might vary in its length. This will always build something that has 3 elements. So in anything where you're building up a long list from kind of smaller versions, cons is more common. Or append. Append is kind of your third option. And append takes 2 lists, but they can be arbitrarily long, and it builds a new list that's got all the elements of this and all the elements of that. So, so append sometimes shows up in recursive cases. Cons, I think, is more often, because oftentimes what you do in your recursive case is you add one more element to whatever you've already built. And then list shows up there less often, I guess. It's always possible that exactly what you want is a 2-element list every time. But if you don't know how long the list is that you're building, then you need cons or append.
Yeah, I mean, so what does cons do, right? So the question is, can we replicate lists with cons? Cons adds 1 element at a time. So if you want to create a list with 3 elements, you enumerate the 3 elements. If you want to use cons, you cons an element to the empty list. You cons another element to that. You cons a third element to that. So it's just a little more tedious, right? You have to do this embedding consing as opposed to list ABC. So you can do whatever you want. It's just sort of where the convenience is. So I think John said it right, which is if you're adding 1 element to a list, the consing and the appending is probably the right way to go. If you're constructing the list from scratch or from multiple elements, probably use list. Although you could use cons, you could use append. It's just a little more tedious.
Okay, so we're taking a look at a problem from CS Mentor's worksheet. This is Mentor section 13. Here we are on page 4, and we're doing the first scheme question, which is called the skip list, which takes in a potentially nested list and a single argument filter function that returns a Boolean when called and goes through each element in order. It returns a new list that contains all elements that return true when passed into the filter function. The returned list is not nested. So if we have a function that finds all the even numbers, and we go through a nested list that's got 1 and then a list within it that has 3, we end up with nothing. Okay? If we go through this nested list, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, and look for all the odd numbers, then we find 1, 3, 5, 7, and 9. But we have to search through the structure of the input, but we don't have to recreate it in the output. We take in this list and this filter function. There's some helper which has 1, 2, 3 different arguments. Kind of the list we have left to process, I think. The list we've built so far, and some notion of next. I'm not sure exactly how these are all going to fit together, but let's skim through and see if we can figure it out. So when we reach an empty list that we're processing, we need to check and see if something else is null, and then do something. Pair is a primitive that tells you whether what you're looking at is a list or not. We don't actually use this anymore, but there's something called list, which will tell you that's not a list and that is. And pair will actually give you the same result. So what's the difference between a pair and a list is something that we don't talk about anymore in the course. There is a difference in scheme, but it's not worth your trouble. So assume this checks to see if this is something that's a list or not. Okay, something might be a list or not. And if so, we do one thing. If it's the case that calling filter function on the first element of a list gives you true value, then I think you want to keep that. Otherwise, filter function returned a false value, we want to discard that.
John, I'm still trying to figure out what next is for. It's not, is it obvious to you?
Yeah, here's what I think is going on is that, let's say you want to keep the 1, and then you see this list. What the heck are you going to do? You're going to make a recursive call on this list in order to find the 3 and the 5.
Yeah.
But then after that, you're going to have to process all this stuff. So while you're processing this sublist, you need to remember what's next, is I think what's happening here.
I see. So list so far in that example would be 1. List would be the list 2, 3, 4, 5, and next would be 6 to 9.
Yeah. I wasn't so sure what list so far is yet. We don't want to build this backwards. Oh, this is a fun one, meaning it's pretty challenging. So what are they doing with all these names? I guess it remains to be seen whether I would have written it this way, but I think that we can start putting some stuff in. So if the car of the list that you're trying to process is itself a list, then you're going to have to call helper on that piece. Now, what do you build? You build, in this example, you'd build a list containing 3 and 5. And the list you have so far, well, let's assume it is whatever we have so far, because we didn't add anything to it yet. And what's next? Well, eventually we have to process the cdr of the list that we started with. That's one way to go. If it's the case that we want to put car list into the result, well, we actually could then process the rest of the list, building up a longer list so far. That's one way to do it. And we process the cdr of the list. Otherwise, we ignore the car of the list and just keep the list so far that we already have. So what happens when we get to the end of a list? There's either a next that we have to process or not. If next is null, then we've really hit the very end, at which point the list that we've built means that we're done. If there's still a next, then we still have some work to do. We want to call the helper on next, the stuff that we haven't processed yet. The list so far that we have stays the same. We've already added stuff to it. And let's see what happens with the next of the next. Yeah. I think we're done with the next of the next. My confidence is not high here.
Yeah, me either.
So, how would we get started? Well, we'd want to process the whole list. We would have built nothing so far. And after we process the whole list, there's nothing left to do. So let's think about what might happen here. We pass in this whole thing as list, and next is nil, and list so far is nil. We see that the first element is odd. And so we construct a new list which appends nil to a list containing the number 1. So now we're building a list containing just 1 as our list so far. We're going to process a list that's everything here without the 1 at the beginning. And this is wrong. And whatever's next should be whatever's next, which currently is nil. So there's nothing like more to do after we finish processing this entire list. Okay, now we get to this tricky case where this is the list that comes in. Its car is itself a list. So we call helper on U, with our list so far being the one that we've already seen, and the cooter of the list being next. That looks good. What happens when we call helper on this? Well, we ignore the 2. That's fine, except for this should be next. We see the 3, 4. Let's assume that it works and puts a 3 in list so far. And then calls on 5 with the right next value. Okay, so maybe I went too fast. When we call U, the next is this 5. And I bet computers would be really good at this. Yeah, let's pretend this isn't nested for a second and see if it works at least with one level of nesting. So if this were just 2, 3, 4, 5, then we'd go through and we'd be adding the 3 and we'd be adding the 5, and then we'd get to the empty list here and we'd see, oh, but null is not next. So I need to call helper on 6, 7, 8, 9 using the 1, 3, 5 I have so far and nothing after that. Okay, so one level of nesting I'm pretty convinced that we've handled. What about 2 levels of nesting? So when there's 2 levels of nesting, we get the 3 and the 4, and we get to this nil. Null, the next from this call would just be like this list 5. So that's where we've gone wrong.
Yeah,
is we've kind of forgotten about, like, when we hit this case the second time, we forgot about the 6, 7, 8, 9 that we needed. Yeah. So the next here can't just be the cooter of the list. It has to be more stuff than that.
Yeah.
It has to be that after we finish with the 3, 4, we have to keep processing a list that starts with 5 and then has 6, 7, 8, 9 after it. Gross.
Yeah.
So I think means that we need to handle the cooter of the list and everything that's after it.
Yeah. That's ugly. I think what was confusing here, this is where I got jammed up too, was the more than one nesting. It's hard to keep track of it. I think this looks more right, but I'm not entirely sure, John.
Yeah, but actually you could write this procedure without a helper and it wouldn't be so messy.
Yeah, that's the part that sort of bugged me, is I found the helper function made it worse.
Yeah, it really did. So if instead we had defined skip list of S as just, oh, and there's some filter, right? If S is null, you're done. If S is a list, then you have to append whatever you get from calling skip list on the car of S using that same filter function onto whatever you get by calling skip list on the cooter of S using that same filter function. if, oh, sorry, my pond syntax is struggling here. Switched over to SQL. If I call f on the car of s and I get a true value, then I should just cons the car of s onto whatever I get by calling skip list on the cdr of s using that filter function.
Yeah, and this is it, right?
And otherwise,
yeah.
I forget the car of s.
Yeah.
Okay. So if we take one of these crazy examples, paste it in here, see what we get. We get a disaster. I did this wrong.
Yeah.
Okay, and then it works. Sorry, so, this base case is, I mean, these like cases are the same, but it's much easier to build a list by kind of putting things on the front and processing the rest in this case, I think, than it is to do it this way, which, you should understand how to do things this way. This is building up a list kind of like you would in Python, appending stuff to the end and remembering what you have left to process. But remembering what you have left to process would be easier for the interpreter to do for you than to be something that you handle yourself. Here, we're handling it ourselves by kind of like building up this list of things that we still have to process. And here, it's just kind of like up to the recursive leap of faith to figure out what's left to process. So if I were actually writing this procedure, I would write it this way. Turns out my way is also more efficient, but we don't talk about efficiency too much in this class. Though I think that something like this would work. Since I didn't type it in, I cannot guarantee that it is right, but it looks kind of right to me. But I have looked at this problem before, but not in a long time, so it's going to take us a while.
All right.
My guess is that this will round out our session for the day because it takes a little bit of time, but we should be able to do it. So here we are in fall 2017, question number 6. The question takes the whole page to describe, and then the code takes a whole page to write. It is about scheme that processes scheme, like a program that writes programs, which is a common kind of question that shows up because, that's really what's new about scheme relative to Python. Otherwise, most of the stuff is the same. So one reason we teach scheme is just to give you practice with all the stuff that you already know, how to write recursion and stuff like that. But another is to show you that you could build programs that write programs. So let's take a look. For this problem, consider a very small subset of scheme containing only if and true and false. Great. Such expressions can be simplified according to the following transformation rules. Here, P, E1, and E2 are scheme expressions in the subset, meaning it's just like ifs and trues and falses. P prime, E1 prime, and E2 prime are their simplified versions. Here's the ways in which you can simplify. If you have if P, E1, E2, and it turns out that P is just true, then you don't need an if expression anymore. You can just write E1, or a simplified version of E1. That's why the prime is there. If this is false, and you know it's false, then you don't need the if expression anymore. You could just have E2, well, a simplified version of E2. And here's another interesting one. If you're choosing between two options that are equal, then you don't need the if expression anymore. You could just choose the first one because they're equal. Okay, otherwise, the if expression has to have a simplified version of the predicate, the consequent, and the alternative, or I guess they're called the predicate, then part, and else part here, which is fine. So you basically take this apart, simplify each of these, and then put it back together with an if in front. Any expression E simplifies to true if E is known to be true, or to false if F is known to be false. Oh, sorry, if it is known to be false. Okay. And then here's an interesting part. In the expression if P(E1, E2), P prime is known to be true while simplifying E1, and is known to be false while simplifying E2. Initially, only true is known to be true and only false is known to be false. Okay, let's look at some examples to try to understand what that last one was. Here's an example. If you write if A, then if ABC, the only way you'd be evaluating this is if A were true, which means you know that A is true, which means you know that this will come out as B. The only way you'd be evaluating this is if you know that A is false, which means that A will come out as false, which means you know that this is E. So this nested if A structure can be simplified to just if A, B, otherwise E. Basically, like no matter what A is, this long expression will be equal to this short expression. I did not write this problem, by the way. This was written by a teaching assistant. Very clever, but also very, very involved. Okay, so I think that the rest of these examples don't really tell you anything new, but maybe I'll pause for a second and see if people have questions about what is going on before I try to dive into the code. A student has to clarify what this question is even asking.
You're basically saying, look, I'm giving you this conditional, and there are certain rules that will allow you to simplify it. If the predicate is true, you just have to evaluate the then clause. If the predicate is false, you evaluate the else clause. And then where things get more complicated is that logic that we just went through, where in the then clause, you know that a certain things are true, right? So your job is basically to take this long expression and simplify it, following the rules enumerated above. Some of them are pretty straightforward, right? So you can imagine that the rule that if P is true, then you simply return the then clause, right? I think where things will get more complicated is the sort of percolating the value of the predicate into the then and the else clause. A great problem, but not for an exam.
Okay, so I think we know what we're after. We're going to have to write code that detects these various conditions and builds the right thing as the result. It's going to be recursive because of this case. An if expression that looks like P, E1, E2 has to be a simplified version of P, a simplified version of E1, and a simplified version of E2. But that recursion is not only going to have a different expression to simplify, but it's also going to have different stuff that's known to be true in order to handle this case of no matter what A is, it's going to be the same here as it is here, and therefore we know it's true here and can get the B out instead of the whole if ABC structure. To simplify an expression is to simp with a context an expression with two with two other arguments, which in this case are what's known to be true and what's known to be false. And simp is the thing that we're trying to implement. And it told us that in the beginning, the only things that are known to be true are true and false. So I think we just write that in here. I didn't write just true and false, but cons t nil and cons f nil because I'm assuming that known t and known f are going to be like a whole list of known true values that will like build up over time. In the beginning, it's just true. In that example we looked at, it would be true and a. And so I've put this into a list. What does it mean to simplify an expression in a context where this is the things we know are true and this is the things that we know are false? Well, a simplified expression is if this thing is a pair, then we assume it's an if expression because that's the only combination that we're allowed in this subset. At which point we call simp if, which, what's nth? I guess maybe we
assume that pulls out the nth the first argument, the second like that parameter.
Yeah, it just gives you one of the elements in a list.
Yeah. So it just cutters through the list, giving you the nth car. Yeah.
Yeah, it must have been defined somewhere, but whatever. Oh, here it is. For convenience, assume nth exists and returns the kth element of the list. Okay, so we're back. This says call simp if on whatever's the first thing, the second thing, the third thing, and the existing known true and known false values. Otherwise, it's not an if, so it's just an expression.
John, can you show, I can't see what's below this a little bit. Can I just see what's coming?
Yeah. What's coming is, if you have an if expression, here's all the stuff you should do.
Yeah, okay.
Let's get this right, and then we'll figure out what we have. So if we have a pred, a then part, an else part, a part that's known true, a part that's known false, then we simplify the pred by calling simp context on the predicate using what we already know to be true and false. To simplify the then part, we have to call simp context on the then part. But in this case, we know that the predicate is a true value.
So this is the part where because you're in the then statement, you know that the predicate must be true, so you have to add it to the knowledge of what is known true for that part.
Exactly.
Right. And same thing, obviously, if you're going to do the, yeah.
And the same is true when you process the else part, then you assume that the predicate is false. If it's the case that the pred is true, then you do simp then. If it's the case that pred is false, then you do simp else. If it's the case that the simp then expression is identical to the simp else expression, meaning after you've done all the simplifying, they're both true, or they're both false, or they're both A, then you don't need to choose between them anymore. You just return one of them. That was one of the rules. Otherwise, it's put together an if expression. We cons the word if. Oh, I guess we know that there's going to be always 4 parts to an if expression. There's the if, there's the predicate, there's the then part, and there's the else part. Whew. Okay,
Yeah.
so this simplified
Right.
expression might still be an if, or it might not be an if. If it's not an if, what is it? It's true. But there's another case when it's true, which is that it's one of the expressions in the known T list. I actually forgot in Scheme how you figure out whether something is contained in a list.
I was just trying to remember that, John. Is there like a member function?
Tricky.
Contains maybe? I don't know if that's built in.
Tried them. Well, let's
member
just pretend
is member an expression?
I got nothing.
All right, let's assume we have it then.
Let's assume we have it, and if we don't have it, then we can figure out a way to hack around it, I guess. But I think the logic that we want is if the known true list contains this simplified expression, then we just want to return true. And if the known false list contains the simplified expression, then we want to return false. Otherwise, we just want to return the simplified expression. Now, if contains didn't exist, what would we do?
I think it might be, it looks like member or memq. Does that look familiar?
Doesn't look good.
No, you know what? Never mind, John. It doesn't matter.
And I don't think it gives us any guidance. Oh, it does. It says use in. So even though in doesn't work, it says use in. So you have to read the instructions, which I didn't do. Okay, so. And this says in takes 2 arguments and the element's supposed to come first, I think. Maybe I should read carefully. If E is equal to a member of the list L. Okay. So this should have gone the other way. Man, it pays to read the directions. That's like the one thing you should learn from this example. Okay, so what have we
but the
done?
directions were like a goddamn page long, John.
So what did we learn? If we had this long description of all the things we need to handle, and we had this long block of code, it was basically a game of figuring out how to handle each part of that long description in a recursive process that will handle a whole nested expression.
I found it easier to work on the bottom part because that was just sort of following the directions for what the various rules were. And then the top part was sort of putting all the pieces together.
It is almost always the case that if there's some like helper function and you're not quite sure what it does, you should kind of focus on that. Oftentimes it can be solved in isolation. And then by the time you're done with this, you kind of know what you're getting back. So at this point, we know we're either getting true or false or A or B or maybe some big if expression. But now we know what we have here. And I always find it's helpful to think about particular examples. We didn't do a whole lot of that this time around, but it was kind of in the back of my mind as I was working. And so you could think of like, oh, what is this thing? It might be A or B or true or false, or it could be a whole if expression.